Thank you for standing by. The call will begin in 4 minutes. Again, thank you for standing by. The call will begin in 4 minutes. Thank you for standing by. We will begin in 1 minute. Again, thank you for standing by. We will begin in 1 minute.
Hello and welcome. Thank you so much for joining us for today's What's on Board Media teleconference for NASA's Commercial Lunar Payload Services Initiative. We call that CLPS. I am Karen Fox with NASA's Office of Communications, and today's conversation will cover the NASA science and technology that will soon be launching aboard Intuitive Machines' second flight to the moon. IM-2, as we call it, is scheduled to launch on a SpaceX Falcon 9 rocket from NASA's Kennedy Space Center no earlier than Wednesday, February 26th. We have three speakers for you today. They are Nicky Fox, who is the Associate Administrator for our Science Mission Directorate here at NASA headquarters in Washington, D.C. We have Nicky Werkheiser, who is the Director for Technology Maturation at the Space Technology Mission Directorate, also at NASA headquarters. And third, Trent Martin, who is the Senior Vice President for Space Systems at Intuitive Machines. After they speak, we will have a chance to answer media questions. You can go ahead and press *1 at any point to get into the queue. And for now, I'm handing it off to Nicky Fox.
Thank you so much, Karen. This is Nicky Fox, the head of NASA Science Mission Directorate. Really excited to be here today to talk about this really amazing lander that's going to head up to the moon very shortly. NASA, as you know, leads the world in space exploration, and of course, for us, American companies play a key role in our establishment of humanity's lunar outpost for the next frontier, Mars. We're so excited that Intuitive Machines will launch this lunar lander to deliver NASA science experiments and technology demonstrations to the moon's surface, and of course, this is their second launch of a lander with us. This is really a key part in our preparation to send astronauts safely back to the moon and soon on to Mars. Right now, our American companies are at the forefront of innovation and discovery through our commercial Lunar Payload Services, and as Karen said, we lovingly refer to it as CLPS. CLPS is a one-stop, all-inclusive delivery service to the moon, where NASA is just one of many customers for that journey. The CLPS vendor, obviously in this case that's Intuitive Machines, they're responsible for payload integration and operations, launching from Earth and landing on the surface of the moon. NASA is investing in commercial delivery services to the moon to enable industry growth and also to support long-term lunar exploration, thereby helping the United States to stay ahead in space innovation. And no other nation has continued to do this. And of course, we all held our breaths and celebrated last year America's robotic return to the moon with the Intuitive Machines 1 lander. At NASA, science enables exploration, and exploration enables science. And so, therefore, NASA Science is just so incredibly excited to partner with our Space Technology Mission Directorate to bring back scientific data in ways never done before using our cutting-edge technology payloads that will be on board the IM-2 lander. As the fourth flight in our CLPS initiative, our payloads on board IM-2 will demonstrate how NASA is using its scientific and human exploration capabilities together to really set the stage for astronauts to go to the moon. You are very excited. You're soon going to hear from Nicky Werkheiser about all the incredible new technology we have on board. But I'm briefly going to mention how this revolutionary technology will enable the extraordinary science that's going to be done in these extraordinary places. We all know that landing on the moon is hard, and NASA's instruments and science experiments will be delivered to a part of the lunar surface that humans have not yet explored. Mons Mouton, a plateau near the lunar South Pole, is a scientifically strategic landing area. You can think of it as the Goldilocks zone for sunlight that can power a roughly 10-day mission while maintaining a clear view to Earth. It is the closest landing site to the moon's South Pole to date, and IM-2 is landing 50% closer than where IM-1 had landed almost a year ago. IM-2 will land in an extremely cold environment that we believe contains volatiles, which are chemical substances that can easily change from a liquid to a solid to a gas. These volatiles may contain trapped water ice and particles from the early atmosphere of the moon and, of course, therefore, the early atmosphere of the Earth. Demonstrating that we can collect these volatiles using the tech demonstrations on board will not only help us better understand the origins of our solar system, but they will also be useful to our future astronauts for in situ resources, including drinking water, breathing air, and creating rocket fuel. NASA Science is also sending up for the second time with Eclipse flight a small, lightweight, inexpensive, yet extremely efficient laser retroreflective array, or an LRA. These help determine the location of lunar landers much more accurately, and we hope to create a large network of these LRAs on the lunar surface to enable more science by better pinpointing the location of key landers and other points of interest. And we will better understand the lunar water cycle using the JPL-led Lunar Trailblazer mission, which is also on board this launch as a rideshare. And that is going to provide insights to us in the form, abundance, and distribution of water in this particular region. I am definitely looking forward to the IM-2 mission launch later this month, and even more excited to see the incredible science that our tech demonstrations deliver as we get ready for humanity's return to the moon and humanity's journey to Mars. So thank you to both the teams at NASA and, of course, to our wonderful partners at Intuitive Machines for this exciting trip to the moon. And with that, I'm going to hand over to Nicky Werkheiser.
Thank you so much, Nikki. I'm giddy to be here today. I know that's not a word we use often, but it's just the truth, to talk about the IM-2 mission. I'm the Director of Technology Maturation in NASA's Space Technology Mission Directorate, as was mentioned. And this has been a really busy and exciting time on the moon as we lay the groundwork for future exploration on the lunar surface and on Mars. In the beginning part of this year, we actually had more than 20 lunar technologies on 3 separate demonstration flights being tested both on the moon and in simulated lunar gravity. And today, we're here to talk about IM-2, which is carrying pivotal in-situ resource utilization, communication, and mobility demonstrations, including NASA's Prime 1 and 2 commercial tipping point technologies that were enabled through a NASA industry collaboration. The tipping points are really special to us. Through this initiative, Space Tech works with private companies to speed up the development of technologies that help us all, that we all need for any sort of lunar infrastructure and a broad range of technologies that could support both government and commercial missions and objectives. The IM-2 mission is particularly special for us in Space Tech as it's largely dedicated to lunar technology demonstrations that are truly foundational to creating a U.S.-led lunar infrastructure. First, I'd like to talk about NASA's Prime 1, which is capable of identifying and quantifying water and other volatiles found in lunar regolith. This is a really important technology demonstration for NASA because it will provide important data to help us better understand the moon's surface and help inform and minimize risk to future in-situ resource utilization missions. It's important to not only NASA, but to the whole ecosystem that wants to explore and utilize resources on the moon, and we will be sharing data from that mission accordingly. In addition to Prime 1, the IM-2 mission is also carrying, as I mentioned, the 2 tipping point technology demonstrations. That will be the Intuitive Machines deployable hopper and Nokia's lunar surface communication system. The hopper will actually enable high-resolution surveying of the lunar surface. It's really cool. It's going to deploy a secondary payload from IM's Athena lander, and then the hopper is a propulsive drone mobility solution from Intuitive Machines that's designed to bypass obstacles and cover a lot of terrain while also moving quickly, which is really a critical capability to support missions both on the moon and other planets, including Mars. And it really enables us to be able to get to areas that we may not be able to do other ways that we really want to explore. We're also thrilled to have Nokia on this mission. Nokia developed a lunar surface communication system that will demonstrate proximity communications between the IM Nova C lander, a lunar outpost rover, and the Micro Nova hopper. It employs the same 4G LTE cellular technology that's used by billions of devices on Earth, and it has a system that's reconceptualized by Nokia Bell Labs to meet the unique requirements of a lunar mission. So that is going to be really cool. The state-of-art demonstrations flying on IM-2 are a product of some of the earliest technologies that we selected through NASA Space Tech's Lunar Surface Innovation Initiative. I hope many of you participate in the consortium as well, where we have such a broad swath of the lunar community. LSII was established in 2019 with the goal of working across NASA and industry, across the whole lunar ecosystem, to ensure that we were developing those key lunar surface infrastructure technologies, and that we could get those developed and proven in time to be incorporated into sustainable missions to the moon. There are several technologies that LSI helped mature for this mission that received early stage funding. I want to mention those two from Space Tech that are now getting infused into lunar demos. So how exciting to see low TRL early work now flying. One that I'm especially fond of is the Water Snooper from Pulley Aerospace that was developed through a relatively low-cost challenge. It was a public challenge called Honey, I Shrunk the Payload and Honey, I Shrunk the Payload, the sequel, that we did in Space Tech along with our science cohorts. And I'm proud to say that they are actually flying on IM-2 as an instrument to one of the SMD demonstrations. So again, I'm very proud to say that this is a very busy and exciting time in lunar and soon Mars exploration, and we are anticipating an even busier cadence to come with more missions led by multiple providers. So we're ready to test and mature these key infrastructures capabilities to prove them out on more areas of the lunar surface and multiply the return of data and return on investment together. So I want to express my gratitude to SMD and Eclipse and Initiative for the leadership in molding this new commercial model that really enables these new opportunities on the moon for NASA and our partners, which has really propelled an integrated and coordinated approach for all of us that are vested in exploration.
Thank you so much. Next up, we have Trent Martin.
Good afternoon, everyone. I am speaking from the SpaceX payload processing facility today as we finish up our integration of our second lunar lander just a short year after our first lunar lander landed on the moon. We call this new vehicle Athena, ADDIE for short. For those of you who followed along the first time, our Odysseus lander, we called him Odie. So this time it's ADDIE. As mentioned, we are landing at Mons Mouton, about 84.8 degrees south, 29.2 degrees east, about 160 kilometers from the lunar South Pole. It's 5 degrees closer than our last landing and the closest anyone will have landed to the South Pole of the moon ever. I will focus a little bit today on the commercial aspect of what we're doing with these missions. In addition to our lander that we're launching on the Falcon 9, we bought the entire Falcon 9, and we were able to offer ride shares to satellites that want to go out to a triangular injection orbit. And in this case, you have a commercial company, AstroForge, who's launching their Odin satellite with our vehicle. So once we deploy the Nova C, Athena, ADDIE vehicle, AstroForge will be deployed, their Odin vehicle, and it is off to do a mission of an asteroid. Through a commercial contract with NASA JPL, are of course putting the Lunar Trailblazer, as discussed earlier, which will fly to the moon and do lunar observations of the moon and water exploration of the moon. And we have another commercial company, Epic Aerospace, who is launching their Chimera orbital transfer vehicle, which is putting a 16U satellite into a geo orbit. On board the Nova C itself, we have, of course, the STMD Trident and M-Solo, Prime 1, as it was called in the Eclipse RFP. We at Intuitive Machines built the deployment mechanism that deploys the drill and M-Solo down close to the surface, within 10 centimeters of the surface, so that the drill can drill into the surface of the moon. We also built the camera and light system that will be used to light the drill pile. Of course, we have the LRA on board. We have the NASA Tipping Point Micronova Hopper, which not only NASA invested in, but also Intuitive Machines invested in. We have named our hopper after software pioneer Grace Hopper, and so we call this vehicle Gracie. Gracie will do 5 hops, one off of the Nova C, about 20 meters or so. We'll then hop around 50 meters or so, doing a parabolic hop. We'll do a long, steady level flight hop, and then hop down into a permanently shadowed region, and then hop back out of the permanently shadowed region. On board the hopper, of course, we have the Nokia LTE as discussed. We have some surface-facing camera systems. We've added commercially a pyrometer from the German Space Agency, and commercially we've added the Pulley Water Snooper, the PLWS, and we've partnered with ESA on that for some of the data that's coming off of that water snooper. We, of course, have the STMD tipping point Nokia system that is not only on the Micronova hopper on Gracie, but also on our rover. The rover is supplied by Lunar Outpost. It is deployed on a deployer built by Intuitive Machines. It, of course, has the Nokia LTE radio and antennas, but it also has a commercial MIT micro rover, which drives around on top of the map rover from Lunar Outpost. It has another pulley water snooper on the rover as well, and a camera system that will allow us to look back at the lander and look at other features on the surface of the moon. We have a commercial rover from a company called Diamond. It's the Yaoki rover, a Japanese company. We have a commercial Columbia Sportswear thermal blanket that we're flying for the second time. We flew one on our first mission. We're flying a second one this time around with Columbia. We have the commercial Lone Star Independence data storage system test that they're flying on this mission. And, of course, we have a plethora of camera systems that will give us good 360-degree surface views from the lander, as well as some surface-facing cameras that will allow us to get views, various views during landing and once we have landed. Our intent is to land at that Mons Luton site around March the 6th for about a 10-day mission. During that time, there is a solar eclipse, so that we're pretty excited about getting the data from that solar eclipse that will occur as the sun passes behind the Earth. We are set up to handle, this is a very large number of payloads that we have on this mission. We're controlling that out of our control rooms in Houston and supporting operations from around the world from different control centers for various payloads that are on the mission. And I will wrap that up and see if anyone has any additional questions later.
Thank you so much to all of our speakers. We will get ready for our questions now. As a reminder, if you are with the media on the call, you may dial *1 to get into our queue. In addition to the 3 speakers who spoke, I'll just let you know we do have 3 people who are also available to answer questions if it's appropriate. The first is Joel Kearns, who is the Deputy Associate Administrator for Exploration in the Science Mission Directorate at NASA headquarters. We also have Jackie Quinn, the Prime 1 Principal Investigator, who is at NASA's Kennedy Space Center. And we also have Terry Klein, who is President of Bell Labs Solution Research at Nokia. So they will be called upon if appropriate. But let me go ahead and start taking questions from the media. First up, we have Marcia Dunn with Associated Press.
Yes, hello. 2 questions. I'm looking for the obligatory cost question, please, from NASA. How much are you investing in this mission, including all of your experiments? And I would like to get some more details on the hopper, Gracie. It's unclear to me. How high can it hop? When you say it's going into a permanently shadowed area, is this like a shallow crater? How deep is it going? I'd just like to get a little more visuals on what it's going to do up there. Thanks.
This is Joel Kearns at NASA headquarters. I'll comment on the NASA investment on the mission. So to take the Prime 1 experiments to the moon on IM-2, that is the Trident drill and the M-SOLO mass spectrometer, NASA has invested a little over $62 million with Intuitive Machines to make that landing. Of course, NASA has more investments than that. There's the investment, the portion that NASA paid of the tipping point for Gracie, for the rocket-propelled hopper. There's the portion of the tipping point that NASA paid for the comm demonstration with the Nokia Bell Labs. So the order of magnitude for that, for the tipping point, and I'll defer to Nikki if I make an error, was on the order of about $15 million for the Nokia tipping point, and I think about $41 million for the Gracie hopper activities. So the actual landing is the sum for NASA's investment is the sum of the numbers that I just gave. Now, in addition to that, as Nicky Fox pointed out, NASA is using this launch, which is that Intuitive Machines bought from SpaceX, for one of our ride shares, which is the Lunar Trailblazer satellite that will go into orbit around the moon. The total cost for the Lunar Trailblazer satellite, including its operations after it's in lunar orbit through 2027, is about $89 million. It's relatively low cost for a lunar satellite, and we also paid a little bit more than that to actually do all our extra checking and integrating it on the launch vehicle, in effect, the rideshare cost. I will not add that all up, although I'll add it up later and make sure we get you the number. But you can see there's one investment we made in the things that will land on the moon, and there's another investment NASA made for what will be dropped off in orbit, the Lunar Trailblazer satellite. And, of course, that doesn't cover the investments that others like Nokia and Intuitive Machines have made. That simply talks about the NASA investment for this landing and orbital opportunity.
And then we had the second question about the hopper. Oh, yes, you were going already. Sorry, I cut you off.
Yeah. This is Trent. I can talk about the hopper question. So to give you a little more details about Gracie. As the hopper hops off, so the hopper sits on the side of the Nova C. There are two rails. The vehicle is released. The launch locks are released, and it launches up off of those rail systems and goes up on its first hop about 20 meters into the sky, and then lands about 20 meters away from the lander. On the second hop, we expect to go around 50 meters altitude, and on the third hop, we'll go about 100 meters altitude. We'll hop down into a permanently shadowed crater, which does not have a name. It's just called Crater H, according to our LRO folks that are on our team. And it is a permanently shadowed crater, however, nearby about 400 or 500 meters away from our landing site. And we will land down in that crater. Once in the crater, if we have communication, we'll continue to communicate with Gracie. We believe, based on our discussions with Nokia, that we might actually still have communication down in that 20-meter depth within that crater. If we do not, however, the vehicle will either go off of a timer. After 45 minutes, it will hop back out on its own, or it will go off of a temperature setting. So if the temperatures reach a minimum, the hopper will hop back out on its own. The purpose of the demo is to show that we can reach extreme environments with technologies other than rovers. So the idea is that if you have a really deep crater and you wanted to get down into that crater, why not do it with something like a drone? So think the helicopter on Mars, right? If you're trying to do something where you can't get there with a rover, why not do it with a rocket-propelled hopper? And so that's the intent of what we're doing with Gracie. When we actually proposed to the tipping point, we only were proposing to do the demo with the camera systems. We added the Nokia, we added the pyrometer, and we added the water snooper after we had started the project with STMD.
Thank you so much. We are ready for our next question, which is from Gina Sunseri with ABC News.
I think this one's for Nikki. I mean, we've got 3 landers hoping to land on the moon in the next couple of months. How does the cumulative knowledge you will get for all 3 of these advance getting humans back on the moon?
Oh, what a fabulous question. Thank you so much. So obviously we have our two landers heading there. We're really excited about the fact that the target launch dates, landing dates, I'm so used to launching. The target landing dates are just a few days apart. And so for us, the excitement of having not 1 but 2 lunar landers carrying our NASA science there at the same time is really amazing. As we do with all of NASA science, we are very cross-discipline, cross-divisional. We do, all of the work. We like to put it together. No one result stands on its own. It's always in the context of our big goals in NASA science. And so just having them at the same time is really incredible. I mean, you heard about all the science that we have on Blue Ghost when we talked about that just what seems like ages ago. It's just a few weeks ago that we talked about that, and now, we're here today to talk about all the spectacular stuff that we have on intuitive machines too. And so really, it is each of our clips kind of has a campaign theme behind it. But when we can get multiple themes on the moon at the same time, then it just really unlocks so much more potential for us at NASA Science.
Sorry, she's about to be put in the queue. If we are having a problem with it. Oh, there she is. She's here now. Amani Guitard, can you hear us? All right.
Yes, hello.
Okay, great.
Sorry about that. My question is, there's so many experiments on this lander that are looking for water, right? That seems to be one of the biggest themes for this mission. So assuming that you get positive results from that, what are the next steps? What are the next plans for using that water?
This is Joel Kearns at NASA headquarters, and others here can also comment on that. So this is we have a lot of equipment on this mission by Intuitive Machines to look for volatiles, which, as Nicky Fox said, are things that include water ice, but they also could be other chemical constituents on the moon. We need to really look at the moon to see what the chemical constituents really are at the surface. And of course, as IM said, they will take their hopper, Gracie, and they will fly into a permanently shadowed region to see what chemicals are in that region, what they can sniff out in the region. There are studies that suggest that in the really big permanently shadowed craters at the south pole of the moon, those are the likely best conditions that if there are volatiles like water and other things that could be of interest, that's where they likely are. This lander will land in a sunlit location, so we don't expect to see ice on the surface, water ice, but we will probably pick up other volatiles at the surface and immediately under the surface. It's going to be interesting to see if the rocket-propelled drone picks up evidence of volatiles, again, which could be water ice, in the small permanently shadowed region that Trent said the hopper will hop into. Once with ground truth on a future mission that water ice is actually identified, as Nicky Fox said, there's a number of potential uses for that in the future on the moon. It could be to provide rocket fuel, hydrogen and oxygen. It could be the oxygen for breathable air. It could be potable drinking water if it's refined. So it's going to be important to understand on the surface of the moon and beneath the surface where these volatiles are, exactly what they are, and on this mission to test the equipment to how to get to them, particularly when they're underneath the surface, be able to get to them and be able to positively identify what the chemical elements are so we can reach conclusions about what these volatiles really are.
Yeah, and this is Nikki Werkheiser. I'd like to add a little bit here and pull some threads on what Joel mentioned in terms of the technology. I know a lot of times we like to categorize things as technology or science, but the truth is it's all one story, right? You can't do science or exploration without having the technologies to implement that. So it's really important, and it's a theme for all that we do in space tech, that we're able to mitigate the risk and increase the TRL maturation of the technologies in the relevant environments at an appropriate scale, so in time for the either commercial or government missions and needs to be infused and scaled up to support those missions. So what I always like to say is we're taking kind of novel technologies and turning them into institutionalized capabilities. And that's really important of what we're doing here with Prime 1, because we're going to be testing out, in particular, the drill, the Trident drill. So in addition to all the things that Joel had mentioned, we'll be measuring the amount of force that's applied to the drill bit while drilling. There's lots of things that we suspect and hypothesize about the moon, but we really need to test it in that environment. We'll measure soil temperature at varying depths. We'll also be able to gather information that helps us understand how the lunar infrastructure interacts with the surface. So how much power is needed to move the regoliths during excavation activities? How do the tools behave in the lunar environment? These are all really important variables that we could invest, billions into the best of technologies, but have, these really important lessons learned that we need to know going into it to make them reliable and maintainable in the environment we are in. So I'll just say that we're working very closely with science. We have ISRU, I think that's plans that we talk a lot about in our Lunar Surface Innovation Consortium in terms of the appropriate path on how to get the technology and the science that we can all use to utilize the resources.
Thank you so much. The next up, we have Marcia Smith with Space Policy Online.
Thanks so much. My question is about the Trident drill, and I'm curious as to how you've tested it already. And I know that we know something about the soil on the moon, and it's a very difficult soil to deal with. So how have you tested it already to be certain that it's going to be able to drill down 1 meter? And I'm curious if you learned any lessons from the Mars InSight mission, where you thought that you understood the Martian soil and it turned out to be very different. Were there any lessons from that you could...
To jump in. So, Jackie, I'll turn over to you to answer that.
Hi, thank you. This is Jackie. So I'm going to address the first question that you posed about how we tested the Trident drill. So Trident stands for the Regolith Ice Drill for Exploring New Terrains. It was built by Honeybee Robotics at Altadena, California, a Blue Origin Corporation company. They originally teamed with us to test the drill, a couple of different drills, in a relevant environment at NASA's Glenn Research Center in a specific chamber that was designed to test the drill in lunar regolith or simulated lunar regolith. So, NASA has invested in concert with USGS to develop different simulants that help us approximate the lunar regolith itself. And we actually use the most relevant physical and chemical characteristic resembling the lunar material from the South Pole region in a test that was performed back in 2019. We actually tested 2 different drills that were developed by Honeybee Robotics, and we tested them in concert with 2 different types of mass, or 2 different sensors on a common mass spectrometer, in order to best position ourselves for making the collective instrument suite that we refer to as Prime 1. So they were tested in a lunar vacuum down to cryogenic temperatures using the most relevant and realistic simulant that we have.
Thank you, Jackie, for that answer. We are moving on to our next question, which is from Leo Enright with Irish TV.
Thank you. A simple question and one not so simple. Simple question, does the Gracie lander have a camera? And secondly, NASA whole strategy around the moon is the search for volatiles at the moment. And you're putting very sensitive instruments on these landers to search for said volatiles, while at the same time, these landers are delivering large quantities of volatiles onto the lunar surface. I mean, there is a jaw-dropping number in a Goddard paper from last month out of the Peregrine mission, which says that, now this is obviously a different scale, but the Starship lander is going to dump something between 70 and 80 tons of water on the moon as it lands, and that's going to cover an area of 100 kilometers.
This is Trent. I can answer the question on the hopper. So Gracie has multiple cameras on board. We use cameras to do our navigation, as well as we have a very specifically dedicated camera that will be looking down at the surface around the vehicle at each landing site, including down inside of the permanently shuttled region.
This is Joel Kearns from NASA headquarters. I'll address your other question. So there are, NASA receives its recommendations and guidance from the scientific community on the scientific priorities for investigating the moon, and the search for volatiles is one of the 3 scientific priorities that NASA works on. Of course, in a wider context of preparing for sustainable human exploration on the moon, if the volatiles include usable water in some form that's easily gotten to on the moon, that will obviously have a great impact on sustainability, for future human exploration. Yes, we look the principal investigators for the particular experiments, do look very carefully at making sure that they can discern, say, chemicals that are present at a site that's landed on, as opposed to chemicals that are naturally deposited near that landing site due to the reaction products of the propulsion from the landers. And I'm also very familiar with the PITMIS publication that was put out the last month, and I'll draw your attention. Of course, that particular lander did not land on the moon, so the instruments were operated in space on the way to the moon, and this became really a test of the operability and the survivability of the scientific instruments. And there were some really good lessons learned that have come out of it that people are looking at. But it's not the same thing as viewing what the reaction products will be on the moon, where there's a surface, it's vacuum, there's a gravity field, there's an exosphere. It's going to be different. But others, Jackie could comment, or other principal investigators could comment, that when you are going to fly down on a chemical propulsive systems all the way to the surface of the moon, and you have to use a rocket to land on the moon. There's no air, there's no reentry, slowing down. There's no Earth-like air that you can use wings or parachutes or anything like that. You have to be able to plan around the fact that you're going to have a propulsive landing, and you have to have your studies set up to take that into account. So I'll throw as an anecdote out there. I think Trent mentioned that there is a Pulley water sniffer on the rover, and there's a Pulley water sniffer on the hopper. So that means that IM, for example, is going to be able to take chemical sniff measurements right at the landing location. Then the rover is going to go to distant locations. They're going to be able to sniff the chemicals out on that. Then they're going to go to the permanently shadowed crater. They're going to be able to sniff it out of that, and they can compare that to the models of what should have been there pre-landing versus post-landing. So they've got a really detailed plan. Yeah.
Let me just add a little bit to that. This is Trent. We use a LOX methane system for our Nova C lander, and the hopper has a hydrazine thrusters. We intend to deploy the rover first. We will have the PLWS measure underneath the lander, the Nova C lander, and we will measure with the Pulley water snooper before we launch Gracie off of the lander. So, and then once we do launch off, we will be able to take additional measurements with both systems. So although the intent of the hopper was to do a demo of the hopper, we are getting some extremely valuable science because of the Pulley water snooper.
Yeah, and this is Nicky Werkheiser. I'd be remiss if I didn't answer just from the global perspective, I'll say, of all of these missions and what we're looking at from a technology perspective, too. I do want to reiterate this question is one of the prime examples of why these early foundational robotic missions are so important, because being completely honest, we will learn a lot of new things. There will be lessons learned. There's really a couple ways you help mitigate that, and a lot of it is what Joel just said. It's a lot of mission planning and science and operational mitigation, and when we're picking our landing sites, for example, and then where we go do our ops, and the instrumentation that we have and the data that we get. But there are also some key technologies. So we have things like a demo that we'll be flying in the future called plume surface interaction, and we do have propulsive elements that are exponentially larger than we had with Apollo. So there will be things that we learn. We've done extensive modeling. We have facilities like Plumbrook. To be honest, there's not that many really large-scale facilities where we can test these type things on the ground at this scale. So we will learn a lot of data, and all of that technology and science informs the next step. So it's an excellent question. It's a really important one. It's one that we talk about a lot. But I think through operations, science, and technology, and a lot of transparency and sharing data, to be honest, with our commercial and NASA communities and subject matter experts, we're able to inform the future missions.
And this is Jackie with Prime One. I just want to say for the mass spec, observing lunar operations, we had a couple of options because the unit is a commercially available mass spectrometer. It's made by Infocon out of Syracuse, New York. And so because we had a lot of opportunity to take a commercial instrument and ruggedize it for spaceflight, we had the ability to choose a sensor type. And the type of sensor we chose to deploy on Prime One is directionally sensitive. And that was key for us because we only wanted to be able to see the volatiles, any of the gases that are sublimating off of the drill pile produced by Trident, and not be able to detect as any of the interferences from any of the other payload activities on board or from any volatiles that are still emanating off of the lander. So to answer that question of, sort of, are you analyzing what you brought with you, we've made great strides in selecting with our commercial partners the right type of instrument, ruggedizing it for spaceflight, and making sure that what we're sensing is what is coming off only the sample that is being brought from the subsurface to the surface for detection of sublimating gases.
Well, with lots of answers to those questions, because there's so much going up on this flight, I'm going to go off to the next question, and it is from Ken Kramer with Space Up Close.
Hi, thank you for doing this. A lot of great information. I'd like to follow up on the drill. How many samples are you taking? What are the depths? And how will you actually analyze the sample? You just talked a little bit about it, but I'd like to know the details. How do you get the sample to the mass spec? Thank you.
I think, Jackie, that's one is for you.
Yes, thank you. All right, so the drill has a capability to extend and get samples down to a meter below the surface. The CONOPS for this are we're going to go down in roughly 10-centimeter bites. We call them a bite. So you can imagine you're going down 10 centimeters, and you're capturing the regolith on the flutes of the drill, the spinning parts of the drill, and then you're going to bring that drill back up to the surface. So you'll penetrate down 10 centimeters, you'll come back up, and during the process of raising the drill, it passively pushes past a brush, and the brushing mechanism basically flings the regolith onto the surface of the moon. And when doing so, it creates a conical pile. So you're looking at, you go down 10 centimeters, bring up to the regolith. Go down to 20 centimeters, bring up that regolith. Down to 30 centimeters, bring up that regolith. So it's a sequential activity. And each time we deposit the 10 centimeters on the surface, we're getting a lot of key both geotechnical data, and we're also getting any volatiles data from the process of sublimation of gases as the mechanical energy that is transported from the process of bringing the dirt up, the regolith up to the surface, and pushing it and off of the drill and onto the surface. Gives it enough energy that the volatiles will sublimate and then be detected by the mass spec. The drill itself has a temperature sensor in the very tip of the drill, and what we plan to do during our operational sequence is to get some subsurface temperature measurements at multiple points, at multiple depths down to 1 meter. So, to date, we have some orbiting assets that are giving us some predicted temperatures, but we don't have an actual temperature with subsurface depth, and we certainly do not have it at this location. So some key activities that we'll be doing is letting the drill just sit in contact with the soil and having the regolith sit on top of the flutes and just coming to an equilibrium temperature and getting that temperature correlated back to eventually, to some of the data that is predicting from orbital satellite predictions from prior missions. So I think the big takeaway here is that we're getting a lot of engineering data from the drill, and Nicky Werkheiser commented on it earlier, where we're getting how much energy does it take us to penetrate down to a meter, how much force are we having to put it to get it to excavate, how quickly are gases evolving. Does some of it happen immediately, and does some of it kind of trail off with time? Those are really important as we look for building systems in the future to harvest those resources that would allow sustained human presence on the lunar surface. When we're talking about building habitats, we're talking about having enough, propulsion, for example, if water was there to make fuel, and how do we go about harvesting it? And this Prime 1 instrument, with the combination of the independent operation of the mass spec along with the drill itself, is really going to give us those first engineering data sets that help us in the future and evolve into future in-situ resource utilization opportunities, infrastructure opportunities, and just sustaining human presence, long-term sustaining human presence on the moon.
I was just going to say also we've got a simulated video that shows everything Jackie just said. It's really cool, so we can possibly share that as well.
I'll try to get you more information about where to find that in a moment and share it here. With that, just a reminder that you can still get in the queue to ask questions with *1. We have about 10 minutes left. Our next question is from Manuel Mazzanti with Exploración Espacial.
Thank you so much. I wonder how long is Athena going to be operating in the surface? And if there's any expectation of extending the duration of the mission in case everything goes according to plan. Thank you.
Yes, this is Trent. I'll answer that question. Yes. Our intent is to land. If we launch, we have a 4-day window for launch. If we launch in the first 2 days of the window, we will land on March the 6th, and we will operate until the sun goes down, which is around March the 16th. So a 10-day mission. With these smaller landers, we really don't have the capability right now to extend beyond the sunlight phase of a lunar day. We can do that already with technologies that we have with our much larger lander. We have our Nova D lander, which can easily go beyond a lunar day. We haven't had a mission yet that requires the kind of mass that we would need in order to add the extra batteries to survive the night. Particularly at the South Pole, the nights can be extremely long. We will get a little bit of data this time because of the 3-hour eclipse that is occurring. So we'll get some data as we go through that eclipse and be able to understand how our batteries are operating during this mission. And we look forward to a future mission where we have a larger spacecraft where we could just put more batteries onto the system and allow us to survive the night.
Thank you. We are moving on to our next question, which is with Anthony Leone with Spectrum News.
Hello, all, and thank you very much for taking our questions today. This message is for Trent. The IM-1 mission was seen as a success, but it did have a bit of bad luck when one of its landing legs dug into the lunar soil and tipped over. So what were some of the lessons that were learned there that will be implemented in Athena to hopefully prevent that from happening again? Thank you.
It's a great question. I appreciate it. IM-1 was a success because we were able to broadcast data from the surface of the moon back to the Earth. But I completely agree that we did end up on our side. We ended up at about a 30-degree angle. So why did we end up at a 30-degree angle? We know exactly why we did. There was an issue with the laser altimeter that we used during the final operation just before landing that would have told us exactly how close we were to the surface. Instead of using the laser altimeter, we were actually just using the camera systems that were on board the spacecraft, and that meant that we landed harder than we intended to land. And because we did, we ended up breaking off a leg and falling over to our side. After the mission, we went through what we call the hot wash. We went through every single thing that went right and every single thing that went wrong on our mission. And for those things that went wrong, what could we do about them? we identified 85 things that we needed to go off and look at. 10 of them were required to be implemented prior to our IM-2 mission. We've actually implemented all 85 of those since our hot wash last March. So we have definitely fixed some of the issues that we had on our first mission. So we don't, hopefully, those won't occur again. Spaceflight is hard, though. Landing on the moon is extremely difficult. Certainly, we will be better this time than we were last time. But you never know what could happen. And I am hopeful that all of you will cross your fingers to ensure we have a little bit of good luck. But technically, we have done everything we can to fix some of the issues that we had on the first mission, and we are excited to give this a try again. Obviously, we need to land upright in order to deploy drills and deploy rovers and deploy hoppers. And so we look forward to that here in just a little less than a month.
Thank you, Trent, for that answer. Moving on, we have Alexandra Whitsey with Nature.
Hi, thanks for taking my call. This is a follow-up on the same issue. If there are various failure modes, like if you land but not perfectly, like what are the scenarios in which you might be able to accomplish some of the surface objectives? Like which of the observations and instrumentation can operate even if you are like on your side or whatever? Can you just walk through a little bit more about what you need to work specifically, and if something goes a little bit wrong, what can you still do even if something goes a little bit wrong?
Okay, this is Trent again. So we actually can land and be up to 10 degrees off in any direction and still complete the mission as planned. If we're further off than 10 degrees in any direction, it may work. We have tested all of our deployment mechanisms with that 10-degree tilt in any direction. If we are off, let's say something happened like last time and we ended up on our side, obviously we would not be able to deploy drills, we would not be able to deploy hoppers and rovers. However, there are lots of instruments on all of those systems that we would still be able to operate. Just like last time, we were able to get quite a bit of the data from the instruments that were on the Odysseus lander, and we were able to send that back to the Earth. One of the issues that we did have last time is because our high-gain antenna was actually not pointed back at the Earth, we were using our extremely low-gain antenna to get our data back. And so we were only able to get about 550 megabytes of data from the surface of the moon last time. We need to get much more than that in order to get some of this higher bandwidth data, for instance, from the mass spectrometer or from the water snooper. And so we can land within a 3-degree angle of our intended angle and have that antenna pointed directly back at our large antennas that we have back here on the Earth. We have a ground network that is our own lunar data network that is comprised of dishes all around the world that we operate for ourselves, and then we've actually sold that into NASA Scan as part of the Near Space Network Services contract, and we're developing relay satellites now. But we have upgraded all of those dishes based on our first mission and some of the bandwidth issues that we had last time, and so we've upgraded all of those nodes in our network on the surface. So that was one of the 85 things that we needed to go off and work, and hopefully all of those will be successful.
All right, we are coming up on time. We have time for 2 more questions, but I'll ask our speakers to give sort of quick answers so we can get through them all. Next up, we have, again, Marcia Smith with Space Policy Online.
Thanks so much. If I could just follow up on the question I asked the first time to Jackie about whether or not there were any lessons that were learned from the Mars InSight mission that discovered that the surface was not at all what they expected, but they did some clever workarounds to at least try and get the drill in. And I'm curious, do you have any contingency plans, even though you only have a 10-day window, in case the drill doesn't penetrate the surface the way you expected?
Yes, we definitely have been training for off-nominal operations, and we do have some technical workarounds and ConOps workarounds. So, we always take a look at lessons learned across the NASA portfolio to see if there's something that we could infuse or gain. That's pretty much our mantra, and we have done that, and we've executed off-nominal sequences and testing with our operations team. The drill itself has some interesting capabilities when it's a percussive augering drill, and it can transition from being wholly augering to a combination of augering and percussive, or just percussive, depending on the hardness of the material that it's attempting to penetrate. Honeybee Robotics did a full set of tests trying to understand the gamut of options that we might encounter, knowing that we were not 100% positive as to where our landing location would be and what we would encounter. So I think at this point we've done as much preparation as far as from the design perspective, taking into account the full range of hardness of media that we might be conveying through. And then we've also developed off-nominal operations to the best of our ability that we're able to go and implement real time. Knowing what we don't know is really going to be key here. You know, it's just you have to be agile and fluid and smart and on point, and just do your very best with what you have at hand. And I think that's the team's very well prepared for that, and Honeybee Robotics will be implementing that plan during the mission portfolio.
And Jackie, thank you so much for saying that. I do want to add one quick thing that's important for everybody to remember, and it's what I love about technology development. Many times we do exactly what we hope to do, and it goes sometimes just like we hoped it would. But often in tech dev, because this is developing these technologies, if we learn what we need to learn, and we could only do that by doing what we're doing now, then that is a success for us, because that is what we had to know to go to the next step. So, like Jackie said, we have all kinds of measures in place, but I think whatever we learn in this environment is going to be very useful.
And then I'll add that this mission, currently we can complete all of our objectives in about 5.5 days. So we actually have some contingency built into the 10 days of the mission, so we don't need the full 10 days. That allows us some extra wiggle room once we get to the surface for things that we just don't know now.
All right. As I said, we were trying to get in one last question. Quick answers, please. Next up is Amani Guitard with InMotion.
Hi, thank you. So this is another question for Trent. Earlier in the call, you mentioned something about a data storage experiment that was being included on the lander. Could you give me some more details about that, please?
Sure. We have a commercial company, Lone Star, that is developing a data storage experiment for their future mission, where they would intend to put a data storage system on the surface of the moon and become the ultimate in secure data storage system. So in this case, it is a computer with a data storage capability. We will upload the data to that, prove that the cybersecurity is working the way we expected it to, download data back from it. It's a pretty exciting experiment that leads us down the path to how do you commercialize cislunar? What could you do? What are some of the technologies that would be useful on the moon outside of NASA science or technology development that we're doing on some of these early missions? What are those missions that lead us down the path where we're doing a fully commercial mission for a company like Lone Star that may want to put a full lander on the surface just filled with computers and allow people to send data back and forth from the moon as your data storage location?
All right, I'm about to toss to Nikki Fox just to wrap it up and bring us home. Before we do that, I just want to remind everybody that you can track information about our CLPS initiative at nasa.gov/CLPS. We will soon be sharing more information about the kinds of media events that will be happening closer to launch. And again, you can watch our broadcast on nasa.gov/live when it happens. So with that, Nikki Fox.
Yeah, thanks so much, Karen. Just kind of wrapping up with what an exciting time it is at NASA Science. Obviously, we all stood together and watched that beautiful launch of Firefly last month, and then getting ready to roll out SphereX, an astrophysics mission, going to track over 400 million, find 400 million galaxies in the universe, riding with it the Punch spacecraft, a set of 4 that are going to kind of give us 3D views of the sun's corona, which hopefully you all saw during the total solar eclipse last year. And then, now today, here talking about the incredible intuitive machines and their second lunar lander, just continuing to do more and more great science here at NASA. And we're really, really proud of our role, NASA Science and NASA Science Technology together. Our role in exploration, science enabling exploration, exploration enabling science, and of course everything we do focused on learning more about the moon, which is kind of our science lab in the backyard. Everything that we learn at the moon, of course, getting ready to send future human missions to Mars. So exciting time in the Science Mission Directorate, as always, exciting time in NASA, and looking forward to seeing everybody at the launch. Go Intuitive Machines 2.
Thank you, everybody, for joining. We will sign off now. Bye.